Give me 1 minute. Okay. Yay. Today there's a lot to cover actually. So there's covering limits to infinity, and then we have to cover continuity, and I'll go over IVT. Yeah. So okay. Let's get started. So let's do limits to infinity, right? So I'll do plus minus infinity. So there's a notion of, not all limits to infinity exist, but if it does and it is a number, then there's a name for it. So horizontal asymptote. It's if limit x goes to infinity, f of x is a, then y equals a is a horizontal asymptote for f of x, right? So you basically, and then same for if limit x goes to infinity, to negative infinity, f of x is b, then y equals b is a horizontal asymptote for f of x. Yeah, so kind of like vertical, right? Vertical asymptotes, it was the x values. It's like the points where you blow up. Horizontal is you take x to infinity. If you get a number, that's a horizontal asymptote. If you take x to negative infinity, you get a number. That's also a horizontal asymptote. So let me just do an example. I don't know. F of x is e to the x. What is the horizontal asymptotes of this function? Well, let's take x to infinity. What is this limit?
No.
It should be infinity, right? So in this case, you just this is the graph, right? But if you don't like the graph, I mean, e is just like 2.7. It's a number, yeah. It's a number bigger than 1, right? There's like 2.7 something. So if you keep raising 2.7 to higher and higher powers, right? Like 2.7 squared, cubed, fourth power, fifth power, it gets bigger and bigger, right? So this should be infinity. So in this case, we don't get anything. Now, what about x goes to negative infinity? What is this? Yeah, I mean, from the graph I drew, it's clear it's 0. But if you don't like it, right? E is just like e is just a number bigger than 1, right? So if the way you should think of it is just think of like 2 to the x, right? like 2 to the negative 5 is, the way you should think of it is 1/2 to the 5th, right? And if you raise a number between 0 and 1 to you just keep taking powers, it gets smaller and smaller, right? Like 1/2 squared is a 4th, and then 1/2 cubed is 1/8. So you sort of see like you're taking fractions smaller than 1, and then you're raising it to the positive power. So similarly, e to the x will go to 0. So you see in this case we have one horizontal asymptote because this thing didn't give us anything. So our horizontal asymptote is y equals 0. Everyone clear on this? Yes? No? Okay. So this should be easy, yeah? So if on your homework midterm, if it asks for find horizontal asymptote, just do these two things, right? Find limit. If limit to infinity gives a number, that's a horizontal asymptote. Limit to negative infinity gives a number, that's a horizontal asymptote. Okay. Now, I want to talk about limits to infinity. Infinity of rational functions. So, infinity of rational functions. So, can anyone tell me what a rational function is? Who remembers? What is a rational function? It should sound familiar. Like, it shouldn't be anything new, but so how about this? Is this a rational function? Like sine x over x squared plus 1? So rational, I mean, think of what is a rational number? It's like something over something, right? So a rational function is something similar, except it's polynomial. Rational function is, instead of number over number, it's polynomial over polynomial. And in this case, we have a very, how do I say it, explicit description of limits to infinity. So before I go over that, if n bigger than 0, what is this limit? So to figure out limits to infinity, all you need to know is this. What is this limit? I mean, just take n to be 1, n to be 2, your favorite positive number. What is that limit? Huh? No, it should be a number, right? not a word. So yeah, 0, right? So yeah, I'm not asking any trick questions. So okay. So from here, right? Once we have this, this is all you need to know to like solve limits of rational functions. So let's go over it. We have 3 cases, right? Since it's polynomial over polynomial, we have case 1, degree on top bigger than degree on bottom, and degree on bottom. Case 2, degree on bottom So by degree, I mean like degree of the polynomial, right? Degree on bottom bigger than degree on top. And then case 3, degrees are equal, right? So once we cover all 3 cases, like once you see like, you know, find limit of rational function on your homework or midterm, that should be like 3 points. Because these are really all 3 cases, right? You can't have like any other. So let's go over the first case, yeah? So let me just do an example. I don't know. I'm going to make it up. Limit x goes to infinity. So the first one is when what? Degree on top bigger than degree on bottom. So let's do x cubed plus, I'm just going to make it up. 26x squared plus x plus 1 over x squared plus 1. Okay. So let me ask you, Ren, if you look at the top, right, when x goes to infinity, which term gets the biggest? Like which term kind of wins, like stands out? No, like on, I mean like on the top. Like if I just look at this, you know, this thing. Yeah, x cubed, right? Because I mean, just think about it. Like it's gonna make a huge difference. Like like 10 squared and 10 cubed is already like a huge difference, right? So think of 100 squared and like 100 cubed, and then like infinity squared, infinity. Like it basically, like when x goes to infinity, like these terms. Let me just say informally, like terms in box are sort of like irrelevant, right? Because x is going to behave like x cubed. And similarly on the bottom, what does this function sort of behave like? Which term wins out? Since I put term in box, let me circle this. So if you look at the bottom, which term sort of wins when you go to, yeah, I mean like constants are like irrelevant, right? I mean 1000 and 1001 makes no difference, right? So you know, so this behaves like x squared, right? And the top behaves like x cubed. So it should behave like limit x goes to infinity, x cubed over x squared, limit x goes to infinity of x. And what is this limit? Yeah. So you should expect the answer to be infinity, yeah, before you even like do it, you know, formally. So from here, like let's actually do it, you know, mathematically, you know. So what I'm gonna do is I'm gonna factor x squared on top and bottom. So 26 plus 1 over x plus 1 over x squared over x squared 1 plus 1 over x squared. These cancel. Now, remember the result we had, I asked above, if n bigger than 0, limit n goes to infinity. Sorry, not n goes to infinity. I hope I didn't write n goes to infinity. Limit x goes to infinity, 1 over x to the n was 0, right? That was from the previous slide or page. So this is easy, right? This thing goes to 0, this thing goes to 0, this thing goes to 0. I mean, the top goes to infinity over 1. So this is infinity. Yeah? So it's nice, right? Because this reduction gave me infinity over 1. If you try doing infinity like right here, you're going to get infinity over infinity, right? And that's sort of undefined, like 0 over 0. Infinity over 1, you know what it is, right? A huge number divided by 1, it's like a huge number. So everyone clear on this? Yes? Okay. So hopefully you see the approach of the next part. So case 2, right? So I have degree on bottoms bigger. So I'm going to make it up. I don't know. X cubed plus 5x squared plus 1 over 3x to the 7th. I don't know. Plus 6x squared plus 5. Okay. Again, let me ask you, what does the top behave like? What does this behave like when x goes to infinity? Good. Behaves like x cubed, right? So let me just write behaves like x cubed. And this behaves like what? Yeah, 3x to the 7th, right? So basically, the short answer would be just whatever has the highest power, right? The highest power will grow fastest. So you should expect, this to behave like limit x goes to infinity, x cubed over 3x to the 7th. This is limit x goes to infinity, 1 over 3x to the 4th. I mean, you could do this several ways, right? You could pull the 1/3 out. You don't really need to, and then, but this is 0, right? So you should expect your answer to be 0, right? Because denominator grows in a way you should think of it like denominator. They both go to infinity, but denominator just goes to infinity way too fast. So if you have a really large denominator, you become really small, right? So let's do it mathematically. Same exact process, right? Factor out x cubed. So I feel like once you get this, right, you already like got the answer, right? I mean, at this point, like, it's just how do you write it formally? So, and then factor out x cubed here. 3x to the 4th plus 6 over, oh, sorry, yeah, in this case, that works. 6 over x plus 5 over x cubed. And then, hopefully you get the process, right? This thing goes to 0, this thing goes to 0, this thing goes to 0, this thing goes to 0. So it goes to like 1 over infinity, and 1 over infinity is 0, right? So again, you just want something where it's clear, right? Like infinity over a number, or a number over infinity, because you know what that is, right? Here, like infinity, if you just plugged it in, infinity over infinity is like really bad, undefined. Okay. Everyone clear on this? I mean, honestly, like on your homework, right? They don't ask you to show work, so you could just stop here. You could say like, oh, this looks like x cubed over 3x to the 7th, so it's like 1/3 x to the 4th. Everyone clear? Yes? No? Okay, so last case, right? So we almost covered like every case. So last case. So the degrees are the same. So I don't know, 5. I forgot the limit. Limit x goes to infinity. 5x. Let's do 4th power. Plus 7x squared plus 1 over 6x to the 4th plus, I don't know, 100x cubed plus 5. whatever. So again, let me ask you, what does the top behave? No. Okay. Yeah. What does the top behave like? When x goes to infinity. Yeah. 5x to the fourth, right? So this behaves like 5x to the fourth. And what about the bottom? Yeah, so I sort of exaggerated the 100 just to tell you, like, the coefficients don't matter, right? Because I mean, the best way to think of why coefficients don't matter is just take the constant, right? If I had like 6x to the fourth plus 1 million, the 1 million is irrelevant when x goes off to infinity, right? That like you see, like, the constants don't matter. so so like, because x will be like way bigger than 1 million. So yeah, so don't be fooled by like the 100. Okay, so this behaves like limit x goes to infinity, 5x to the fourth, 6x to the fourth, 5 over 6. Yeah, so you should expect the answer to be 5 over 6, right? So again, mathematically, how do you do it without getting undefined? Well, what I'm going to do is I'm going to factor out x to the fourth. Right, so these cancel. Now this goes to 0, this goes to 0, this goes to 0, this goes to 0. So this pretty much goes to 5 plus 0 plus 0, which is 5. 6 plus 0 plus 0, which is 6. So this is 5 over 6, right? So let me just say, let me go back, right? So now we could conclude, right? In case 1, when degree on top is bigger, it goes off to plus or minus infinity, right? In our example, it was plus infinity, right? But if there was like a minus sign, it could have gone to minus infinity. If degree on bottom is bigger, it goes to 0, right? Because I mean, like 1 over, if degree on bottom is bigger, it behaves like 1 over x to the n. And if degree was equal, what was the answer? Well, it was the leading coefficients, right? Leading coefficients of highest degree, right? So what I mean by that is you look at the highest degree term. This is the coefficient. Look at highest degree term. That's the coefficient, right? And that was your answer. So that should cover all cases. Okay, is everyone clear on this? So none of you should get these questions incorrect on homework or midterm or final. Everyone clear? Okay. So now let's talk about continuity. I mean, if you don't need to show your work, then yeah, you just. I mean, same for the other ones, right? If the degree on bottom is bigger, if for me, if I just see the degree on bottom is bigger, I just write 0. I mean, unless like the questions say show your work, but I mean everything's online, right? So if they just want the answer, why waste your time? So okay. Uh, so let me just recall, right? Limit x goes to a, f of x is L, right? So we say the limit when x gets close to a is L. So remember I said it doesn't matter what f is at a. Do you all remember that? Like limits only care about, when you approach a, not the value at a, right? But then let me ask, what if the limit was the value at a? So what if limit x goes to a, f of x is f of a? So we have a definition for this, right? So if this is true, we say f is continuous at a. So no, this means a few things, right? It means that there are three things I'm assuming. I'm assuming f is defined at a. First off, if you're not defined at a, you can't be continuous. Two, I'm saying limit exists, right? And three, I'm saying limit, this is the important part, limit is equal to f of a, right? Because you can have limits existing, but it's not f of a, right? It's something else. So no, continuity is a bit stronger. Everyone good? And then we say discontinuous just means not continuous. Do not ask me why it's called discontinuous. I like rather than like uncontinuous or something. I'm not good with English, so okay. Everyone good? So there is a nice notion. It is true, but do not take this as definition, right? So continuity, right? Continuity in one dimension, right? Which is what we're in, one dimension / single variable. There's a definition where if you graph, you don't lift hand off paper. Right, so I'll sort of explain what I mean by that. Yeah, so let's go over examples of functions that are not continuous, right? So I actually didn't use this slide. Okay, not continuous, examples of not continuous functions. Right, so so picture-wise, right, here is not if we use the informal definition, this is not continuous. Why? So if we use that wrong definition, right, it's kind of right, but if I draw this on paper, right, I have to lift my pencil to go here, right? I can't unlift, I can't just stay on the page, right? Because if I stay on the page, how do I go up? I have to draw a line and then go up, right? But I don't want this line, this vertical line. So like to draw this function, right? To draw this, you have to lift your pencil off the paper, right? So, or if you're on iPad, lift your Apple Pencil off your screen. So, okay, so that's like picture wise, but so in this case, right, why is it not continuous? Well, let me call this one. Let's call it, so let's see which one it doesn't satisfy, right? So one exists, right? So if I call this, so not continuous at 0. So it's certainly one, it holds, right? It's defined at 0. Right? Let's call this 1 and 2. So like f of 0 is 2, right? If we call this the function f, 2, does the limit exist? Well, it doesn't, right? If you take limit x goes to 0 from the right of f of x, right, it's 2. Agree? Because I'm approaching from the right. So this is 2 limit x goes to 0 from the left. Well, what is that? Well, it's 1. Yeah. So limit doesn't exist. And I mean, the third part automatically fails if 2 fails, right? I mean, the third part says limit is f of a. Well, limit doesn't exist. So yeah. Everyone good on this? So I mean, and so you might ask, okay, what about something where limit exists, but it's not continuous? Well, something like this would be an example. Again, I have to lift my pencil off the paper. So let's call this 1. This is the point 0. Something like this. Yeah. So at 2. Right? So this is not continuous at 0. Again, picture-wise, it's because you have to lift your pencil off the paper. 1, it's defined at 0, right? Hold on. Let me close the phone. So 1 is certainly true, right? F of 0 is 2, right? I'm defining it to be 2 at 0. Now, do limits exist? In this case, it does, right? Because limit x goes to 0 from the right is 1. Limit x goes to 0 from the left is 1, right? So, but the problem is, so the limit exists. So limit x goes to 0 is 1. But the problem is it's not equal to f of 0, right? Because f of 0 is 2. So 3 fails. Right? So limit exists, but it's not equal to the number we want. Right? We want it to be the actual value of the function. Everyone clear on this? Yes? No? So all the functions, the nice functions are continuous. Like, I mean, like all the nice functions like y equals x squared. This is continuous, right? I don't really need to lift my hand off the paper to draw the parabola. So yeah, so all the mostly all wherever they're defined, right? Like natural log it's continuous from like open interval 0 to infinity. Obviously, you can't natural log a negative number, but wherever it's defined, it's continuous most of the time. So I guess I didn't go over the case where it's not defined. So just take y equals 1 over x, not continuous at 0, right? I mean, you don't even need to work on this, right? Because in this case, 1 fails. Because, I mean, or we call this f of x. F is not defined at 0, right? So, I mean, if it's not defined, and certainly limits don't exist, right? So, remember, continuous means it's the value of the function at 0, right? But f is not defined at 0. So it's so this is easy. Yeah. And then like even if you try to say like let's call g of x to be 1 over x for x not 0, and make it a number at 0. I don't know. Say it's 0 at x equals 0. This is still not continuous. So even if you try to just say it's a certain point, right? Like 1 will hold, but 2 it doesn't hold, right? Because limit x goes to 0, 1 over x. I think I went over this many times, right? This is does not exist. And again, if you try to do it picture-wise, I have to lift my pencil, right? From here to the bottom part, you have to lift your pencil. There's no way to work in one quadrant and then not lift your pencil and go to another quadrant. So yeah, so does everyone sort of understand, continuity and so forth? Yes, no. Okay, so if I give you a piecewise function, right? So a lot of times, piecewise function. If the inside functions are continuous, right? So let's say, I don't know, x squared plus 1 for x less than 0. It's 2x for x between 0 to 5. Yeah. And then, I don't know, let me just say, it's going to be like, I don't know. Let me think. Sine of x for x bigger than 5. Yeah. So each of these functions are continuous, right? I mean, they're continuous everywhere, right? If you just draw it. But I'm changing functions in between, right? So you can see, like, since all these functions are continuous, I mean, you could certainly graph all of these without lifting your pencil off the page, like, and then if I go back, you can certainly graph sine without lifting your pencil off the paper. So, like, from here, right, the only problem is when I change functions, right? So when I change from this to this and this to this. So you see, these are the problematic points, right? So it's possible to not be not be continuous at, say, 0 and 5 in this case. So what you would do is say, okay, what is limit x goes to the left of f of x, right? So from here, right, I need that this has to be f of 0, right? So remember, to be continuous at 0, limit x goes to 0, f of x is f of 0, right? And in this case, right, what is f of 0? Well, at 0, it's 2 times 0, which is 0, right? Because at 0, we are this function, right? So this better be 0. But when I take limit from the left, right, I'm approaching with numbers smaller than 0. So this is limit x goes to 0 minus of x squared plus 1, and this is 1, right? So you see, it's not continuous at 0. Because this limit, because on one hand, I mean, this is even worse. Like, limit x goes to 0 from the right. The limit to 0 doesn't even exist. So 2x, which is 0. So in this case, not continuous at 0, right? So you need the limit to exist and for it to be the value of your function, right? And then same for 5, right? Like here, limit x goes to 5 of from the left, right, of f of x. So I'm approaching with values smaller than 5. So I'm right here in the middle. So I have limit x goes to 5 minus 5 minus of 2x, and that is 10. And I don't care, what sine of 5 is, right? But if I go from the right, question for everyone. can sine of 5 be 10? Is that possible? Is that possible? So yeah, why not? So what is sine bounded by? So, I mean, I don't know what sine of 5 is. I would need a calculator. But yeah, it's bounded by -1 and 1. So, I mean, I don't know what sine of 5 is, but I know it's not 10. So, I mean, picture-wise, right? Let me just draw the picture. At 0, sorry, that's my dad. So, at 0, right, before 0, we have a function, right? At 0, it's 1, right? So maybe it's like a parabola, going upward, right? Sorry, this should be open circle. Sorry, open circle. Pretend. Let me erase them. So at 0, this is open circle because I'm not equal to. And then 2x, right? The line 2x is given by something like this, right? But let me erase. So it starts at 0, goes up to like 10. Right? So you see here, there's like a jump, right? Kind of like you're jumping from the open circle to the closed. And then at 5, I don't know what sine of 5 is, but it's like a wave. Maybe it's like somewhere here, but it's certainly not 10, not at 10, right? So here is like some open circle, and then that's sine. So there's a jump here, right? So you sort of see if for continuous functions, right? When I switch functions, it's possible to jump, and that's what causes the discontinuity.
Call from
Sorry.
Kelvin.
Okay, so let's move on. So for the rest of this class, let me go over IVT. So I want you to spend a minute. So let me just draw 2 points for all of you. This is B. This is B f of B, and then this is A f of A. Yeah, so this is A. Okay, so what I want you to do, if you don't have your pencil, get a pencil or paper. Draw your favorite function. I mean, don't make it boring like a line, but I mean, you can, but draw your favorite function. It has to be a function, right? So it passes the vertical line test, but you don't lift your hand off your paper. So we want continuous functions, right? So draw your favorite function that connects these 2 points, but you don't lift your hand off the paper. So I will give you like maybe 15 seconds. So 1, 2, 3, 4. Okay, so I'll just draw mine. I don't know. Let's make it. Okay, no matter what function you drew, right? I'm gonna ask you something. If you choose any y value in between, so this is obviously this is f of b, right here is f of a. If you choose any y value in between, you're gonna notice there's a point that maps to it. Like here, right? There's the points right here, right? So we call this, there's a point that maps to it. So any y value in between will get hit. Do you all notice that on your paper? Yes or no? So when you draw your function, what you're going to notice is every y value in between gets hit. Yes or no? Yeah. So this is it's pretty much, this is what IVT says. So for continuous functions, so informally for continuous functions, you hit every y value in between. That's hopefully you know what B/W means. So you see, this is false for not continuous functions, right? So if I do something like this, right, I don't hit oh really sorry, I didn't intermediate value theorem. Sorry, I thought I defined it. So basically, if you read it right, it's just saying you, just like the name says, you hit all intermediate values, right? You hit all y values in between. So if you look here, you don't hit y values here, right? For this continuous function, but for continuous functions, you must hit every y value in between. Yeah. So that's the informal way of defining it, right? So I guess IVT. I didn't really look it up, but I would just define it. Let f be continuous on AB, right? For any, so how do you say you hit every y value in between? Well, for any y value n, right? For any n, there is a c. For any n, let me just say in between f of a, f of b. There is a c such that s dot t for such that such that f of c is n. Right? I believe that's like the statement. I didn't really look at the book, but so it's something like this. So yeah, so this is this is mathematically how you would say it, right? Pick any n, pick any y value. There's a point that maps to it. So why is this useful? Well, there are IVT questions. I'm not sure if we're going to ask that because it's sort of like a word short answer word problem. But you basically use it to show there's a root. So x to the fifth minus sine of x. Show show this has solution. So how do you show this has a solution? Basically, this is saying x to the fifth minus sine x has a root, right? But this function is continuous. Is continuous, right? So I can use IVT. So how do I say there's a point that equals 0? My n, my capital N is 0 in this case. I need to show there's a c, right? So how I do this is it's easy, right? Find a point above 0. Find a point below 0. And then IVT says I get every value between it, right? In particular, I get 0. So give me a point where f of that point is bigger than 0. Any suggestions? You could be as wild as you want. I mean, I'll just start you off. Yeah, like 98, right? 98 to the fifth is certainly bigger than 1. I don't care what sign of 98 is. The biggest it could be is -1, and I mean it's bounded by -1 plus 1. This is bigger than 0. And f of, let's do -98. Oh, sorry. This c is in AB, right? So it's in between AB. So -98 to the fifth minus sine of 98. This is smaller than 0, right? So IVT says there is a c. So know how I word it. There is a c in between the 2 points you plug in -98 to 98, such that f of c is 0. Yeah, and then you're done. So this is really powerful, right? It basically says there is a root. No, it doesn't tell you what c is, like you don't know what the root is, but you know there is one. So that's what IVT like is strong for. It guarantees roots without even telling you what the root is. So everyone clear on IVT. I'm sort of went fast because I'm running out of time, but hopefully IVT is clear. Yes, no. Okay, cool. Yeah, so hopefully that should cover stuff for the next homework if it's posted. I heard it's not posted yet, but okay, yes. What is your question? Oh, yeah, I don't know because I don't post the homework, so